When you see Mars, is it just a red dot or a future home? Scientists have studied Mars for decades, exploring ways we might one day live there. Mars lies within the Sun's habitable zone, the region where temperatures allow for liquid water. With the right technology, life on Mars is possible. And Mars holds vital resources: iron, copper, aluminum, and more. Everything needed to build and sustain industry. These raw materials could power future colonies. They could even be shipped to Earth, supporting industries through space mining. As Earth's resources inevitably run low, Mars offers new space and supplies. But how will we actually get there? A mission to Mars begins here on Earth, where we must plan for everything: the payload, essential equipment, life support systems, transport modules, and more. Inside the spaceship, primary systems include MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which breathes in carbon dioxide and exhales oxygen while also functioning as a fuel oxidizer. Next, water systems. Aboard the spaceship, 98% of water must be recycled. How? The water processor assembly, whose key components include the urine processor assembly and the brine processor assembly. These systems work together to process clean water for the astronauts. With this ready, what will power our ascent into space? The answer? Krusty, or kilopower reactor using Stirling technology, a nuclear reactor power system. However, still in development, Krusty is currently only able to produce 10 of 40 necessary kilowatts. The fuel that powers the ship will be in liquid form, giving the spacecraft solid control and efficiency when compared to hybrid or solid rockets. When launching, the oxidizer releases liquid oxidizing agents down into the combustion chamber, while the liquid fuel also makes its way down. When in the chamber, the igniter sets a chemical reaction, releasing large amounts of energy that give the rocket enough explosion power through the nozzle to lift off to the red planet. Utilizing an SLS rocket intended for human expeditions through space, the rocket activates its thrusters. It takes around 2 seconds for the 4 RS-25 engines, reliable engines that provide high efficiency, to reach full performance, and roughly 8.8 million pounds of thrust to achieve liftoff. Once the rocket is off the ground, it starts accelerating rapidly. Our spacecraft will be split into different compartments, each with a specific role. First is a sleeping compartment, allowing for quality, uninterrupted sleep, which is crucial to maintaining a strong mental health. For maintaining physical health, the exercise compartment will provide machines such as a treadmill to be used by the astronauts. A mission to Mars needs more than fuel. It needs a complete food system. Essential food groups including fruits, vegetables, proteins, grains, healthy fats, and dairy are all covered. Additional vitamins and minerals are added as needed to meet nutritional demands. These ingredients combine into balanced meals to keep the crew strong. Finally, after the months-long journey, the ship has successfully landed on Mars. Immediately, the habitat must be developed. The Mars city requires a precise system to support a society, from commodities to structures to locations. Dust storms are extremely frequent on Mars, and in these storms, wind gusts can reach a speed of at least 68 miles per hour. Hence, buildings and structures should not exceed 2 stories to mitigate risk of collapsing. Another factor that must be accounted for when developing a city is radiation. All structures will be constructed with sulfur concrete, since Mars has ample sulfur and aggregate, and also serves as a passive shield for radiation. To further combat the risk of radiation, a thick layer of regolith lies on top of the sulfur concrete, another accessible passive shield for structures on Mars. And on top of that, multiple sheets of polyethylene will be attached to the structure to maximize protections against radiation for safety. For living, homes will be in villages to shorten distance between facilities for overall streamlining. Each house has a simple design, with small viewports to see sunlight for personal health. An airlock system would be needed to move in and out of the house, because Mars's atmosphere is composed mostly of carbon dioxide. The internal atmosphere would be kept at a lower pressure than Earth's atmosphere to reduce the strain on the building. Even so, the house would have to be specially reinforced against the internal pressure. These homes, however, are not the only place for human settlement. In Mars's agriculture test site, a geodesic greenhouse is wrapped in 2 meters of frozen water ice. Inside, hydroponic racks grow diverse plants for consumption. A cyanobacteria melt pond produces oxygen and fixes nitrogen into ammonia for future soil. An Arctic tundra bed grows dwarf willow and poppy. The white hydrogel holds water, while their roots stabilize dust for next-gen modified crops. Crops aren't enough. We need protein. But packaged meat spoils quickly, and poultry needs gravity, water, and constant cleanup. Neither is sustainable for space. Emerging solutions offer better alternatives. Microbial proteins like algae grow efficiently in compact bioreactors. Insects such as crickets thrive on waste with minimal resources. In the near future, aquaponic systems might raise fish and crops together. These approaches move us closer to sustainable Martian living. The industrial facility of Mars uses two main energy sources, solar and nuclear. Solar works during the day while nuclear provides a steady supply. This is the Sabatier facility. Here, carbon dioxide from the air and water from ice caps are turned into essential resources. In the electrolysis tank, water splits into oxygen for breathing and hydrogen for fuel. In the Sabatier reaction chamber, carbon dioxide combines with hydrogen to make methane and water. The facility powers a colony with oxygen, fuel, and energy. On Mars, we need two types of rovers working together. A pressure radiation shielded Mars SUV, the manned rover carries scientists and workers across the surface. Its frame uses carbon fiber and aluminum alloys with layers of polyethylene to shield from radiation. An onboard multi-mission radioisotope thermoelectric generator powers both rovers in all conditions by converting heat from radioactive decay into energy. Before the crew even moves, the autonomous rover maps the route. Using infrared sensors, an IMU, and wheel odometry, it generates a 3D model of the terrain and marks the safest path forward. These rovers are workers, transporting samples and equipment between the habitat and mission sites. While the manned rover focuses on delivering people to mapped out locations, the autonomous rover ferries supplies and sets up gear ahead of time on top of its mapping purpose. It uses similar materials and MMRTG power, but swaps seats and controls for a radiation-hardened computer, capable of thinking on its own when Earth is 15 minutes away by radio. Together, they extend each other's reach. Autonomous units work ahead with the manned rover following their paths, bringing human minds to sites made safe and ready. Resources are also an important step to ensuring survivability on Mars. Without them, humans wouldn't stand a chance against the Martian environment, which has temperatures that can fluctuate anywhere between 70 degrees Fahrenheit, or 20 degrees Celsius, and negative 225 degrees Fahrenheit, or negative 153 degrees Celsius. Additionally, humans wouldn't be able to produce food, make the trip back to Earth, create useful products, or even create any products in the first place. Since transporting essential resources from Earth is impractical, however, executing mining operations directly on Mars becomes necessary and highly crucial. Fortunately, Mars is composed of many of the resources already utilized regularly on Earth. Many of its more commonly found resources, particularly certain clay and basalt-based minerals, can be used to produce concrete, which can then be used for construction. Certain gemstones can be used for industrial production of steel. Tridymite, sulfur, and ferrihydrite can contribute to subsistence as insulation, fertilizer, and water purification, respectively. These resources are widely available, especially at Olympus Mons and the Jezero and Gale craters, locations that remain mostly untouched, even by rovers, but have been major points of interest among scientists for years, with Olympus Mons being the largest volcano in the solar system and the two craters potentially being ancient lake basins. Additionally, scientists report that Mars has subsurface ice deposits so large that, if they melted someday, could cover the entire planet in a shallow ocean of water. By conducting mining operations in those regions, we could find a reliable source of water and potentially uncover billions of years of history. In this way, mining operations could be tied not only to survival on Mars, but also major scientific milestones waiting to be achieved in the future. In the event that a sustained human presence on Mars becomes necessary, a wide range of new economic and governance guidelines must be determined, particularly those related to currency, economic regulations, and government structures. A new Martian-specific currency will be introduced to reflect Mars's unique economic conditions, independent from Earth. Tying it to an Earth-based currency will subject the Martian economy to irrelevant fluctuations or destabilizing economic shocks. To ensure stability and trust, the currency will be resource-backed. Thus, an energy standard is chosen, as energy is a fundamental and universally required resource for everyday life. By linking the Martian currency to units of energy, the system will align economic growth with industry and infrastructural development. Additionally, funding and labor will be prioritized for life support infrastructure, sustainable food systems, and habitat safety to ensure that the Martian colony is expanding stably as necessary. As for governance, Mars will adopt a technocracy-democracy hybrid, gradually transitioning from more emphasis on technocracy to democracy as the population grows. This means that a cabinet of scientists and professionals will be appointed, potentially by a collaboration between the UN and ISS partner agencies. In conjunction with this, elected representatives will join the decision-making process. As time progresses, the technocracy cabinet will transition to becoming policy advisors, supporting a democratic system that is grounded in technical expertise and citizen input. Returning to Earth will not be an easy task. It involves careful planning, advanced technology, and precise timing. First, we'll bring back physical samples of Martian rock and soil. Next, we'll send back mission logs to help researchers better understand Mars and improve future missions. Lastly, to prevent any contamination, these materials will be handled in sterilized and secure containers on their way back to Earth. To power the rocket, we will use ISRU, taking carbon dioxide and hydrogen in situ resource utilization to produce rocket fuel. Once launched, the spacecraft will follow the Hohmann transfer orbit, a fuel-efficient path taking from between 6 to 9 months. Returning from Mars isn't easy, but with the right tools, it's possible.